Okay, so hi everybody. What we're going to do here is continue our lecture covering chapter 26 of the textbook, which is all about DC circuits. And the next topic in this lecture is Kirchhoff's rules. So let's get into this. So to sort of set the stage for you, why we're talking about Kirchhoff's rules, let's think back to the previous two chapters and how many tools that we've developed to analyze what's going on in the circuit. For instance, if I want to know what sort of current is flowing in the circuit or how much charge is building up on capacitors in a circuit, we've developed a number of tools to give us those sorts of answers. And just to sort of recap that, we have series and parallel circuit elements. So we've applied this idea of combining different devices in series and parallel. We've specifically applied that to resistors and capacitors. So simplifying a circuit by combining things in series and parallel is a useful tool. It can help you solve for things like the current or the charge. We've also developed Ohm's law, which just relates voltages and currents. But for some DC circuits, as we're going to find out, these tools are just insufficient. It's not going to be enough to solve for, let's say, an unknown current in the circuit, just to use the rules that we've developed up until this point. And we need something a little bit more sophisticated. And that's where Kirchhoff's rules come in. Okay, so Kirchhoff's rules are pretty simple to wrap your head around. There are just two of them, just two things to remember. And the first thing is the junction rule. So let's just read what this says here. The sum of the currents entering a junction must equal the sum of the currents exiting the same junction. So in other words, if we write this as an equation, we take the summation of the currents going into a junction, that has to equal the summation of the currents going out of that same junction. Okay? The second rule is called the loop rule, which says the sum of the changes in electric potential, that's delta V, around any closed loop of a circuit must equal 0. So if we write this as an equation, the summation around a loop of all the delta V's is equal to 0 for any part of the circuit you look at. Okay, so let's expand on each one of those. And in particular, I want to give you a sense of why each one of these is true. And then we'll talk about how to apply these rules to solve a problem. To solve, let's say, for an unknown set of currents in a circuit. So for this, we're going to go over to the document cam. And how about we start with the junction rule? Okay, so let's actually sketch out a picture of what it looks like when there are currents flowing in or out of a junction. So this is just one possible example, but let's say we have 3 different wires, like this, which meet at this point, so that will be our junction, and then merge into a single wire after that point. Okay? And then let's just put some currents in this diagram. Let's say we have, for simplicity, 1 amp of current going into the junction here, 1 amp of current going into the junction here, and then 1 amp of current going into the junction here. So the question is, how much current do I have flowing out of this junction in this segment of wire here? Well, the way we're going to figure this out is by using conservation of charge and the fact that we don't expect any charge to be building up at this junction point, right? There's no particular reason why charge would be piling up here at this junction point. Okay? So this gives us the idea that if I have some amount of charge flowing into this junction point, it has to just flow out of that junction point in order for nothing to be building up right there. So if I have 1 amp plus 1 amp plus 1 amp of current flowing in here, the sum of the currents flowing into the junction is 1 amp plus 1 amp plus 1 amp. That gives us 3 amps. Kirchhoff's junction rule says that the sum of the currents flowing out of that junction is also 3 amps. And in this case, we just have one current, this one right here, flowing out of the junction. So that's 3 amps. Okay? So the whole reason behind the junction rule is any charge that flows into a junction point should just flow out of it so that no charge builds up at that junction point. That's the idea. Okay. Now, the next one is the loop rule. And again, I want to give you guys some kind of sense as to why the loop rule is true. And, well, let's start with this. The loop rule has to do with changes in electric potential, or delta V, as we go from one point on the circuit to another. And let's draw the simplest circuit in the world, which is just one battery, okay, with a negative and a positive terminal connected to a resistor. Okay, so something like this. And so this says, if we pick some point on this circuit, let's call this point P. And then we go in a loop around the circuit in any direction. So I can take the loop going, let's say, clockwise like this, or I can take the loop going counterclockwise like this. It doesn't matter. As long as I end up at that same exact point where I started, the loop rule says, if I take the sum over the loop of my delta V's, I'm going to get 0. And in this context, it makes a lot of sense, because let's say I want to take the loop starting at point P, going clockwise. Well, the delta V for that entire loop is going to be the electric potential at point P minus the electric potential at point P, which is 0. In other words, it's just the same exact electric potential at the start and the end. And if you recall, this is just a consequence of electric fields being conservative. That's something we learned back in chapter 23. But let's actually show this in a little more detail. Let's think about what the electric fields in this circuit actually look like. Well, this is the battery up here. And I know there's an electric field inside of the battery, and I know which way it points. It points from the positive to the negative terminal of the battery. That's how electric fields work. So let's call that E battery. But I also know that there's an electric field in the wire itself, which is why there's current flowing in this circuit in the first place. There's an electric field in the wire pushing the charges around. And as we saw back in chapter 25, this electric field just goes along the length of the wire in the direction of the current. So there's E wire. Okay, you guys remember how you actually calculate delta V? Well, it's minus E dot dL. Which means if I'm going against the electric field, this negative sign tells me that if I'm going against the electric field, I have a positive delta V. And then I'm going with the electric field, then I have a negative delta V, if you recall. So how do I actually take the sum of delta V's for this loop here? Well, it's basically going to be this. Start at point P, and then I go across the resistor. So that's going to be a delta V for my resistor. And then, if I keep following this loop, I have another delta V going across the battery. And by the loop rule, we should be expecting to get 0 here. And this makes a lot of sense, because if I'm going across the resistor, I'm going in the same direction as the electric field. So this delta V for the resistor is negative. But if I'm going across the battery, I'm going against the electric field, and this would be a positive delta V. So the negative and positive delta V's for this loop here, again starting at point P going clockwise all the way back to point P, the positive and negatives just cancel out to give you 0 delta V overall. So that's how it works for a really simple circuit like this, but you can actually apply this to more complex circuits. Alright, so those are the rules. And so I want to just give you 2 quick examples of how we can apply this. Let's start with the junction rule. So as we said earlier, the whole way this works is the sum of the currents going into a junction equals the sum of the currents going out of a junction. And this just naturally follows from conservation of electric charge. So in this case, I've got 3 different currents, I1, I2, and I3, going into this junction. And that's where multiple wires meet up. And then I have 1 wire flowing out of this junction like this, carrying a current I4. So we have 4 different currents to think about. How do I actually write down an equation relating the currents in this case? Well, I have to think about which of these currents are going into the junction. Well, it's pretty clear just based on the directions that are shown with the arrows here, that it's I1, I2, and I3 going into the junction. So, on the left side of the equation, where I add up all my currents going into the junction, I have I1 plus I2 plus I3. On the other side, I look at the currents that are going out of the junction. There's only one of those in this case, but of course there can be more in general. And I4 is the only one flowing out, so we just set this equal to I4. Okay? So that's how you would generate an equation relating different currents that are in a junction. And then let's take a look at the loop rule. Okay? And again, this follows from the fact that E fields are conservative or path independent, as we talked about just previously. So let's take this as our example circuit where we're going to apply the loop rule. Okay, what's happening here is you just have a simple circuit with a battery and 2 resistors and just 1 current that flows in a loop around that circuit. So let's generate our loop rule equation by starting at this point labeled right here on the bottom left side of the circuit. And let's take this loop going clockwise. So that means we're first going to go across the battery like this, then we're going to go across resistor number 1 like this, and then we're going to go across resistor number 2 like this, and then back around to that point where we started. If I add up all those delta V's for the loop, I'm going to get 0. That's the idea. And that equation looks like this. When we go across the battery, that's our first term, we're going from the negative to the positive terminal. And as we learned about in chapter 25, this means we have a voltage increase going across the battery if I'm taking it in this direction, from negative to positive. So there's a positive V term right there. The next thing I do is I go across this resistor. And in this case, I'm going across the resistor in the direction of the current. And as we learned about in chapter 25, that means we have a voltage decrease, or a negative delta V. But independent of the sign, the exact magnitude of that is just given by Ohm's law, I times R. So what do we have? I have minus I times R1 for this voltage decrease going across the first resistor. And then by the same exact logic, we have minus I times R2 going across the second resistor, and then we're back where we started, so we can then set that equal to 0. That's how it works. Now, keep in mind, the choice that I made to take this going clockwise was completely arbitrary. We could have done it in a different way. In other words, we could start at this point and then take the loop going counterclockwise in the exact opposite direction, and it's still going to give you the same equation. So let me just show you how that works. So this time, we're going to take the loop going counterclockwise. So what are we doing? First, we're going across R2, and then we're going across R1, but crucially, now we're going against the current. And then the last thing we're going to do is go across the battery, but something's different from before. We're going from the positive to the negative terminal. So our loop rule equation is going to look like this. I start by going across resistor number 2, but again, since I'm going against the current, that's a positive voltage, so plus I times R2. And then another positive voltage for here, going across resistor 1, I times R1. And then I have a voltage decrease if I go from the positive to the negative terminal of a battery, because I'm going in the other direction. This is minus V. All right, and then back to where we started. That's the complete loop. That equals 0 when I add up all those voltages. So I hope you can see that this is a very useful set of tools to figure out, let's say, what a current is going to be in our circuit, to solve for, let's say, an unknown value of I, or multiple unknown values of I. If you write down these equations, you can solve for the currents. And so I just want to summarize Kerkoffs rules with sort of a general set of guidelines to help you solve problems when Kerkoffs rules are involved. Okay? So this is sort of a step-by-step process that you can use. And the first step is you've got some kind of circuit that you're trying to analyze. The first thing you should do is draw a diagram of that circuit if you don't have one already. And on that diagram, label all the different currents in the circuit. And when you label a current, we typically do this by showing an arrow giving the direction of the current, and then labeling that with some kind of variable, like I1 or I2. And that means with that arrow, you're picking a direction for the current to go in. Okay? But before you solve the circuit, you might not know which direction the current is actually going in. So you just have to pick some direction, draw some direction for the current, and stick with it. If you chose the wrong direction, and it's actually going the other way, what's going to happen is when you make your calculation, it's going to come out negative. All right? So if you chose the correct direction, the current comes out positive. If you chose the wrong direction, it comes out negative. And I'm going to show you an example of that in just 1 second. Okay, so step 1 is complete. You've got your diagram. All of the different currents are labeled. You've got a direction for each one. And then step number 2 is this. Just look at the diagram, count how many independent currents that you have. Okay, so how many different currents are there to solve for is going to determine how many equations you need to generate to actually solve the system. Okay, so this is like one big algebra problem where we have a bunch of different unknown variables. We need the number of equations to equal the number of unknown variables. Okay, so step 3, generate as many equations as you can using the junction rule. Because typically, the junction rule is going to give you simpler equations than the loop rule. So use the junction rule as many times as you can until you just run out of equations. And then go on to step number 4, which is write down some more equations using the loop rule. Okay? So remember, the loop rule says when we add up all the voltages across a circuit in a loop, where we start and end at the same point, we get 0. So what we have to know and get really good at doing is calculating delta V, or the voltage across a particular element of the circuit, for resistors, capacitors, and batteries, because those are the circuit elements that we've seen so far. So just to remind you, if we're going across a resistor, delta V is given by Ohm's law. It's I times R, and we have to know if the sign is positive or negative. We have to really get this right. So remember the rule, delta V is positive if we're going against the current, and then by the same token, it's negative if we're going with the current. Okay, so whenever we have a resistor in our loop rule equation, we know exactly how to treat it, I times R, and then the sign that you attach to that just depends on whether we're going with the current or against the current. Okay, another thing you might see in your circuit is a capacitor. So we learned way back in chapter 24 that the voltage across a capacitor is given by Q divided by C. So the charge on the capacitor plates divided by the capacitance. And again, we learned that there's a certain sign convention that's associated with this delta V. So delta V is going to be positive if we're going from the negative to the positive plate. On the other hand, if we're going from the positive to the negative plate, our delta V is going to be negative, right? So just, again, you have to decide which sign it gets depending on which direction across the plates you're going. And then the last thing is battery, and well, typically we're just going to be given what the battery voltage is. It's not something we'll calculate. But we have to get the sign right. And the sign works pretty much the same way as for the capacitor, right? If we're going from the negative to the positive terminal of a battery, then our delta V is positive. Okay, if we're going the other way, if we're going from the positive to the negative terminal, then our delta V comes out negative. Okay? So these are things to keep in mind when you write down a loop rule equation. Alright, so once you've come up with all of your equations using the junction rule and the loop rule, and again, you need as many equations as you have unknowns, the rest is just algebra. So step 5 is just to solve your system of equations algebraically. Now, this can be kind of time consuming, but it's pretty straightforward to solve a system of equations algebraically. Okay, so with that said, we know what the rules are. Hopefully you have some kind of sense as to why they're true. And now you have some kind of sense as to how to apply them. Let's do an example. So in this example, we're going to look at the circuit shown in this diagram right here. And it has two different batteries. So battery number 1, battery number 2. Each one of these batteries has an EMF and an internal resistance. And also in this circuit we have three different resistors, R1, R2, and R3. Okay? So the lowercase r's in this are going to represent the internal resistance of the battery. The uppercase r's are going to represent just the load resistance of some device. So for instance, you can imagine these are light bulbs. Okay, so what are the numbers? Battery number 1 has an EMF of 80 volts and an internal resistance of 1 ohm. Battery number 2, that's this one in the middle, has an EMF of 45 volts and an internal resistance of 1 ohm. The resistors have the following values of R. So R1 over here is 20 ohms, R2 over here is 40 ohms, and R3 at the top of the circuit is 30 ohms. So here's what we're going to do. We're going to use Kerkoffs rules to find every single current in this circuit. Okay, so that's the circuit we have. First thing we need to do is label all of the different currents that appear on this circuit diagram. And as I said before, we have to choose a direction for each one. Okay, so let's get some kind of sense as to how many different currents are there to actually solve for. Well, if you recall, if we have a single conducting path in a circuit, let's say this lower branch of the circuit, the current is just the same everywhere in this branch because everything is connected in series. Okay? But if I have a separate path, let's say the one in the middle, that might have a different current. And then if I have a separate path from that, let's say the one at the very top, that might have a different current still. So there are actually three different currents for these three different branches of the circuit that we need to think about. And again, I'll show you what they are. Let's call the current that flows in this lower branch of the circuit, let's call that I1. And let's just arbitrarily say that it's going to the right. Okay? We might be wrong about that, but let's just choose a direction and then stick with it for our calculations. Okay, I2, that's going to be the one in this middle portion of the circuit. Again, all of the elements in this middle portion of the circuit have the same current going through them. And we'll arbitrarily choose the direction to be to the left. Okay, we might be wrong about that, but let's just choose that for now. And then finally, I3 is going to be the current in the top portion of the circuit, and we're going to arbitrarily say that that's going to the right. Okay, so three different currents. What do we need? Three different independent equations to solve for the currents. Okay, so we've labeled the currents, we've established that there are three, which means we need three independent equations. Okay, so the next thing we need to do is come up with those equations, and let's start with the junction rule. Okay, let's identify on our circuit diagram where do we have a junction, and point P that I've labeled over here is an example of a junction. Okay, because we have multiple different wires coming together at that junction and multiple different currents coming together at that junction. So what does the junction rule say? It says we take the sum of the currents going in, and that equals the sum of the currents going out of the junction. So based on how we drew everything here, which current is going into the junction? Well, it's I2. That's going into the junction at point P. Okay, and then I1 and I3 are going out of the junction. Okay, so the current going in, which is I2, is equal to I1 plus I3, the ones going out. Okay, so the equation is I2 is equal to I1 plus I3. That's the junction rule. Okay, step 4. Now we're going to move on to the loop rule. So we have one junction rule equation. That means we're going to have two loop rule equations. So the idea is, look at any loop in the circuit, right? You can say, maybe I want to choose this loop for the bottom portion of the circuit right here. or maybe the top portion of the circuit right here, or maybe just the outer portion of the circuit, the biggest possible loop. You can choose any one of those loops. You can take them going clockwise or counterclockwise. It doesn't matter. We just need two equations, so let's just pick any two loops and generate some equations that way. So the first one I'm going to do is the top portion of the circuit. We're going to start at point P, and then we're going to go around the loop clockwise. Okay, so let's generate that equation for the loop rule. If we start at point P, which is right here, and then we follow this loop around going clockwise, the first thing we're going to hit is this resistor, R3. Going across the resistor in the same direction of the current gives us a negative voltage minus I3 times R3. Okay? So if we continue on this loop, the next thing we're going to go across is this battery, which is epsilon 2 for its EMF. We're going from the negative to the positive plate, so we know that's a positive voltage. So I'm going to write positive epsilon 2 going this way. And then the next thing is I go across the internal resistance of the battery. This time I'm going in the same direction as the current, so it's another voltage decrease when we're going in the same direction as the current. So that's minus I2 times little r2 for the internal resistance. The last thing we go across is this resistor big R2 before we get back to where we started. And again, I'm going across that resistor in the direction of the current, so that's minus I2 times big R2. So we've completed the loop. We can just set that to 0. So that's one equation. Okay, we need one more because we've got two equations so far. We need 3 to solve for all 3 currents. So again, we can just pick any loop in the circuit that we want. How about we do the outer loop, the very outermost loop of the circuit, starting at point P, going clockwise. Okay, so what does it look like when we take this loop? So I'm starting here at point P. I'm going to go around the outer loop of the circuit clockwise. The first thing I'm going to hit is resistor number 3, which is exactly the same as before. That's going to be minus I3 times R3. Okay, but since I'm taking this bigger loop now, the next thing I go across is R1. But look at how we drew the current I1. It's going, if we're going this way, we're going against the current. Okay? So going across resistor number 1, I have a positive voltage because I'm going against the current, which is I1 times R1. All right, the next thing we go across is little r1 right here. And again, we're taking this across the resistor against the current, so we have another positive I1 times little r1. And then finally, the last thing we do before we end up back at point P is we go across the EMF of this battery, which is actually going from the positive to the negative plate. So remember, when we go from the positive to the negative plate of a battery, that is a negative voltage, or a voltage decrease. So that's it. Now we're back at point P. That's the complete loop. So I know that all of these things have to equal 0 when I add them together. Those are our 3 equations. So the rest is just a little bit of algebra. Not too bad. So how about we go ahead and work that out. Okay, so here is our 5th step. We've got our 3 equations. We wrote them down symbolically. So let's plug in every known value that we have, and then work out what the solution is using some algebra. Okay, so what were we given? Epsilon 1 was 80 volts, so plugged in 80 volts wherever epsilon 1 appeared. Epsilon 2 was 45 volts, little r1 was 1 ohm, little r2 was also 1 ohm, and then the big R values are 20, 40, and 30 ohms for those 3 different resistors. Okay, so that's our system of equations that we need to solve. So let's do the algebra on the document cam. So what are our equations? We have minus 30.0 times I3, and then plus 45.0. And the next term was basically, we'll take
the two resistance values, which were 1 ohm and 40 ohms, you can just combine those to be 41 ohms times I2. And that equals 0. So that's our first equation. And in the second equation, we have minus 30, this time also times I3. And then we had two resistance values multiplying I1, which were 20 and 1 ohm. So we can combine those like before to just be 21.0 ohms times I1. And then minus 80, that equals 0, so that's equation number 2. And then the last one, actually it was the first one we wrote down, but let's call it equation number 3, is the junction rule equation, which is I2 equals I1 plus I3. Okay, those are the three equations. A lot of different ways we can go with this, but I'm just going to do whatever comes to mind first, which is how about we sub in, here, sub equation 3 into equation 1. In other words, equation 1 has an I2 in it, and what I'd like to do is eliminate the variable I2. The way I'm going to do that is by subbing in I1 plus I3. So that gives us the following. We have minus 30 times I3 plus 45, and then minus 41 times I2, which I'm subbing in as I1 plus I3. And that's our equation. So let's expand out what's in the parentheses. Oh, that's also equal to 0, by the way. That's the full equation. We have minus 30 times I3 plus 45. And then I have minus 41.0 times I1 minus 41.0 times I3, all equal to 0 once again. So let's combine the two I3 terms. I have one at the start of the equation, another one at the end. So when you add these together, you get minus 71.0 I3, and then minus 41.0 I1 plus 45 equals 0. Okay, so the next thing we're going to do is, using what I just wrote down, we're going to sub out I3. So let's start by adding 41 I1 to both sides, subtracting 45 from both sides, and that will give us this. Or actually, no, let's do it this way. Let's just add 71 times I3 to both sides. So it puts it over here. So we have 71 times I3 equals minus 41 times I1 plus 45. Okay, so the last thing we need to do to solve for I3 and then be able to substitute it out somewhere down the line is divide out 71. So you're going to have, as your first term, let's see, minus 41 over 71, which we're going to have as a decimal, 0.5775, but with 3 sig figs, times I1. And our second term is 45 over 71 positive, which as a decimal is 0.6338. And there you have it. By the way, I'm leaving off the units because it's just going to get too messy, but we know it's going to work out in amps at the end. Okay, so we're going to take what we just wrote down and sub this into the one equation that we haven't even touched yet, which is equation 2. So let's see what that gives us. So equation 2 is, we have minus 30 times I3, but this is what we're subbing in for I3 right here. We have 0.6338 minus 0.5775 I1. That's the first term. The second term is plus 21.0 I1. And then minus 80.0 equals 0. Now we're at a point where we have just a single variable in a single equation, so we're almost there. We just have to sort of do the algebra. So first, let's take minus 30 and distribute it into these parentheses. So our first term is going to be minus 19.01 for this term. And the second term is going to be positive, because I have these two negative signs, when you multiply these two factors, 17.33, and that's multiplying I1. And then the rest we'll just keep as is. It's 21.0 I1 minus 80.0 equals 0. And let's see, what can we do with that? Well, we have these two factors which can be brought together, the ones that multiply I1. So we're going to have, for that, 38.33, if you add these two numbers together, times I1. And then if you add these two numbers together, the ones that are just constant factors, we have minus 99.01. Okay, so to solve for I1, here's what we do. Just add this 99.01 to both sides, and then divide by 38.33. So what we have is I1 equals 99.01 divided by 38.33, and that results in, let's see, 2.583 amps. And actually we'd run round that off to 2.58 amps, like that. Okay, so now that we have one current, the rest of them just sort of fall in line, because if we have I1 using this result right here, so I'll draw a little arrow showing we're using this result. Just plug in I1 and you get out I3. So I3 is equal to, we got minus 0.5775. Multiply that by I1, which we just found to be 2.583, and then add that to 0.6338, which gives us for I3, let's see, what does that give us? Minus 0.857 amps, which rounds off to about 0.86 amps. So notice how the first one we solved for came out positive. What that's telling us is the direction we assumed initially was correct. This one came out negative, which means the actual current is flowing in the other direction. So I3, we assumed the wrong direction to start off. Okay, and then the last thing is, from the top of the page, we have a way of calculating I2 from the junction rule. It's just the sum of I1 and I3, and we have to add those together. All right? So I2 is equal to I1 plus I3, and that means we have 2.583 minus 0.857, and the result of this is 1.726, which would one round off to a nice 1.73 amps. Again, this one came out positive. That means the direction we initially assumed was correct. All right. So with all that in mind, let's summarize the findings. We get the following values for I1, I2, and I3, just as we said before. And if we look at what this looks like on our circuit, given that one of the currents came out negative, okay, I3 came out negative, it means the direction we assumed was wrong, as I said. So if we actually want to show what's going on, okay, the directions that we assumed for I1 and I2 were correct, so that means down here in the bottom branch of the circuit there's 2.58 amps of current flowing this way. There's 1.73 amps of current in the middle portion of the circuit flowing this way to the left. And then of course 0.86 amps of current flowing across the top portion of the circuit to the left in the opposite direction that we assumed. Okay? So again, don't worry about trying to guess the correct direction for a current at the beginning. It's all going to come out in the math at the end. All right. So that was an example of how to use Kerkoffs rules. And I want to give you guys one to work out on your own. So as usual, what I'd like you to do is look at the question here. Think about it for a minute. Pause the video. try to work out your own solution, and then once you have an answer, come back to the video, and then let's see if you got it right. So in this question, we have a circuit shown on the bottom, and we're going to do the following things to the circuit. We're going to, in step 1, apply the junction rule at point P. So we're going to come up with an equation by applying the junction rule at point P. The second thing we're going to do is apply the loop rule to the large outer loop of the circuit, starting at point P, going clockwise. Okay, so that means we're going to start here, go all the way around the circuit like this, run the outer loop, and then come back to point P. That's going to be number 2. Then number 3 is another loop rule. What we're going to do is we're going to apply it to the small leftmost loop of the circuit, starting at point P going clockwise. So we start here, go down, then around this way, and then back to point P going clockwise. So again, those are just arbitrarily chosen loops. You could have done other loops for number 2 and number 3, but I just want us all to have the same equations so we know we're getting it right. Okay? So let's work it out. So right here, I've copied down the picture. And on that picture, there are some currents that are pre-labeled for you. So I1 is going to be this current in the leftmost portion of the circuit. And we're just going to assume the direction for now. Let's assume it's going clockwise like this. And then I2, let's just assume it's going down in that middle portion of the circuit. And then I3, we're going to assume it's also going clockwise. Okay, so let's do those 3 equations. Let's just generate the equations. So equation number 1, again, is to apply the loop rule at point P. And point P, by the way, is up here. That's the junction point we're talking about. So remember, the loop rule says the sum of all the currents going into the junction equals the sum of all the currents going out of the junction. In this case, we only have one current that's going into the junction, that's I1. But we have 2 currents that are going out of the junction, which is I2 and I3. So that's it. That's our first equation. Our second equation, this is a loop rule where we're going to start at point P and then follow the outermost loop of the circuit until we get back to point P going clockwise. Okay, so this is, oh, I'm sorry. Step 1, we were applying the junction rule, not the loop rule. Okay. So step 2, now we're applying the loop rule. Apply the loop rule to the outer loop of the circuit. Okay, here it is. So if we start at point P, the first thing we do is we go across this 12 ohm resistor. Now we're going across that resistor in the same direction as the current, so that's going to have a negative sign, negative I3, and in this case I'm just going to plug in 12 ohms. That's the resistance. So I times R, again that's Ohm's law for resistors. The next thing we do is we go across this battery. And which direction are we going? We're going from the negative terminal to the positive terminal, which means we have a voltage increase happening of plus 36 volts going across this battery. The next thing we're doing is going across this 24 ohm resistor in the same direction that the current is flowing, which means we have a negative voltage minus I3 times 24.0 ohms. Okay, the next thing we do is go across this resistor, the 36 ohm resistor. We're still talking about current I3, and we're still going in the same direction as the current as we follow the loop. So we have minus I3 times 36.0 ohms. Okay, we're not done. We have to now follow this all the way around the outer portion of the circuit. Over here, we're going across a 12 volt battery from negative to positive, so that's positive 12.0 volts. And there's one more thing to do before we complete the loop, which is to go across resistor number 1, to go across this 56 ohm resistor with current I1. So we're going in the same direction as the current in this case. So we have minus I1 times 56.0 ohms. Okay, finally that equals 0. So that's a pretty big loop rule equation, but we had a lot of different circuit elements to go across before we completed the loop, so a lot of different terms there. Okay, now look at equation number 3, which is we're going to apply the loop rule to the small leftmost loop of the circuit. So I'm talking about right here on the left. So we'll start at point P, go clockwise as before. And so the first thing we encounter as we go across this loop is this 48 ohm resistor. Now in this case, we're going to cross it in the same direction as the current I2. So I have minus I2 times 48.0 ohms. And that's the voltage decrease across this resistor. The next thing we encounter is this battery. Now in this case, I'm going from the positive to the negative terminal of the battery. That means I have a voltage drop, yet again, of minus 24 volts. It's a negative sign. And then to complete the loop, we go across the 12 volt battery, but in this case we go from negative to positive, so that's going to be a positive 12 volts. And then the last thing is we go across the 56 ohm resistor in the same direction as the current, so it's minus I1 times 56 ohms. What does that all equal? Well, 0. That's the whole point of the loop rule, is we sum up these voltages in a closed loop of the circuit and we get 0. Okay, so that's equation 1, that's equation 2, and that's equation 3. Now in this case, because it's a little bit tedious, as you saw in the previous example, to go through the algebra, I'm just going to skip over that part. These are the equations. So you have 3 unknowns, I1, I2, and I3, and you've got 3 independent equations. So if you solve the system, here's what you get. For I1, you should be getting 0.142 amps. Then for I2, you're going to be getting something negative, which is minus 0.415 amps. And then for I3, you're going to get something positive, which is positive 557 amps. So again, the fact that one of these currents, I2, came out negative, it just means the direction we assumed was wrong. It's actually not going down, it's going up. But that's the value. Okay. So let's keep going with these. The next example I want to do is, it involves jump-starting a car, which is something you may have encountered at some point in your life. Basically, here's what's happening. A good battery is being used to jump-start a car with a weak battery. The good battery, which is the one we're going to label number 1 up here, has an EMF of 12 volts, or sorry, 12.5 volts, and an internal resistance of 0.02 ohms. So those are going to be labeled as epsilon 1 and lowercase r1. The weak battery, which is right here, has an EMF of only 10.1 volts, so it's getting weaker over time, and an internal resistance of 0.1 ohms, so more internal resistance than would be ideal. So each copper jumper cable that we attach the good battery with over here is 3 meters long, 0.5 centimeters in diameter, and has a resistivity for copper of 1.68 times 10 to the minus 8 ohm meters. So we're going to have actually resistance for the jumper cables to consider in this problem as well. Okay. The whole reason the car isn't starting, by the way, is in your car you have something called a starter motor. So this is actually an electric motor that gets your car's engine running after it's running with the starter motor. After the starter motor starts it running, that is, you can just have it continuously run using gasoline, but you need to get it started with this electric motor. That's the idea. So we need some kind of current running into this starter motor, or else it's not going to actually start the car. All right.
So there are two questions here. The first one is, if we only have the weak battery connected, okay, so just forget everything at this top of the circuit. If only the weak battery is connected, how much current do we have going to the starter motor? Okay? And then, as a follow-up, let's say we do have the good battery connected, so this is in the circuit, how much current do we have going to the starter motor? So as you can probably guess, if only the weak battery is connected, we're not getting enough current going to the starter motor, but if we do connect the good battery to help us jumpstart the car, we're going to get a lot more current going to that motor, and it can actually start the car. Okay, so let's work it out. So we have two situations here. The first situation is we only have the weak battery connected and nothing else, so this is what the circuit looks like. We have RS for the starter motor, we have little r2 for the weak battery's internal resistance, and epsilon 2 for its EMF. So we know which direction current is going to flow. It's going to flow off the positive terminal, around the circuit, and then loop back around to the negative terminal. And this is a really simple circuit. There's only one single path for current to flow in, so we only have one current. So I can just apply the loop rule to the only loop that's in the circuit, and this is what the equation would look like. Let's say we're going to start here at this point. We're going to take the loop going clockwise. The first thing I do is I go across the EMF of the battery. So I have positive epsilon 2, since I'm going from the negative terminal to the positive terminal. The next thing I do is I go across the starter motor in the same direction that the current is flowing. So I have minus I times RS. And then the last thing that happens is I go across the internal resistance of the battery, which would be minus I times R2. So all I'm trying to do here is figure out what the current is. So epsilon 2 can be equated with, if we take these two negative terms to the other side and add them, I times RS plus R2. Just factoring out the common factor of I. So the current that we're looking for, just divide out this thing in parentheses, is epsilon 2 divided by RS plus R2. And what do we get? So epsilon 2, that's the weak battery's EMF, is 10.1 volts. And then we have the summation of these two resistance values. One of them is 0.15 for the starter motor. The other one is 0.10 for the internal resistance. And these are measured in ohms, but you can think of that as a volt per amp. So we're getting a current measured in amps. So you do the calculation, and you should be getting 40.4 amps. Technically, we're going to keep two sig figs here because of the two sig figs in the denominator. And so we could round this off to a nice 40 amps. Okay? So the idea is, apparently 40 amps is not enough current to actually get the car started, which is why we're going to jump start it and connect the second battery. And this is going to help us actually get the current we need. So now my circuit is a little bit more complicated. Remember, I'm connecting the good battery using jumper cables like so. And then there's the starter motor. And so how many different currents are going to actually be here in this circuit? Well, there are going to be three. Okay, there's going to be one current in this top portion of the circuit, and let's call that I1. And let's just arbitrarily say it's going clockwise. There's I2 in this middle portion of the circuit. Let's just say it's going to the right. And then there's I3 right over here in this bottom portion of the circuit. And keep in mind, I3 is exactly what we're solving for. We want to know how much current is going into this starter motor. So ultimately, we want to find I3. And those are the three currents. Okay. So there's actually one thing we have to kind of calculate as a side calculation first, which is what is the actual resistance of the jumper cables
which are connecting the two different batteries? Well, the jumper cables are going to have a resistance given by the equation rho times L divided by A. So rho is the resistivity of the copper, L is the length of the cables, and then A is the cross-sectional area of the cables. So any sort of wire or cable, generally we're going to just assume it has a cylindrical shape to it, just a really long and narrow cylinder. And so the area is going to be a circle, because the cross-sectional area that the current is actually moving through when it's in the jumper cables is a circular cross-section. Okay, let's put the numbers in. For the resistivity rho of copper, we have 1.68, 10 to the minus 8 ohm meters are the units. Now the length of each one of these cables is 3 meters, so that's L. And then we divide by pi times our radius. Well, we actually are given the diameter, which is, the radius is half the diameter. So I'll take 1/2 times 0.50, but 0.50 centimeters was the diameter. We want to get this in meters, so a centimeter is 10 to the minus 2 meters. So we square that. That's the calculation to do to get the resistance of the jumper cables, and it's really not that much. It's 0.00257 ohms. Okay? So we're going to need that value for what comes next. Let's just get it out of the way. All right, now on to Kerkoffs' laws. What we're going to do is look at the circuit that we just constructed. Think about how we can apply the loop rule and the junction rule. So how about we start with the junction rule, and let's pick a junction to choose. How about right here is point P, that's going to be our junction. So let's apply the junction rule at point P. Okay, what does the junction rule tell us? It says that the sum of all the currents going into the junction equals the sum of all the currents going out of the junction. Well, if we look at the way we drew the currents here, the only one that's going into the junction is I3. Okay, if you follow I3 around, it's going into point P. And then there are two currents, which are I1 and I2, going out of the junction. So I have to add I1 plus I2 for the two currents exiting or going out of the junction. Okay, that's our first equation. Clearly we're going to need two more. So the two other equations are going to come from the loop rule. So for the first loop rule equation, how about we take this upper portion of the circuit right here, and how about we go clockwise? And how about we start at point P? All right, so the first thing we're going to do, if we take this upper loop going clockwise, just like this, is we're going to go across the resistance of the jumper cable on the left side. So the current is I1, the resistance is RJ, and it's negative for this voltage because we're going in the direction of the current. The next thing we're doing is going across the internal resistance of the good battery, which is the one on top. And again, we're going in the same direction of the current, so this is minus I1 times little r1. Next, we go across the EMF of the good battery from negative to positive. So that's a positive voltage, positive epsilon 1. And then the last thing here, at least on the top portion of the circuit, is we have minus the same current I1 times RJ, because we go across this second part of the jumper cables connecting the weak battery to the good battery. Okay, so we're not actually done with our loop. We have to get all the way back to point P, which means we're going to go across this middle part. And the first thing we're doing is we're going across the EMF of the second battery. This is the weak one. But in this case, we're going from positive to negative. So we have minus epsilon 2 for that. And then the last thing we have is we're going across the internal resistance of this battery, but we're going against the current, which means we have a positive voltage, I2 little r2. That equals 0. Okay, so that's symbolically what the loop rule equation looks like for this upper portion of the circuit. So let's do another loop rule equation. And let's apply it this time to the lower portion of the circuit. And let's take this one going clockwise. Okay, so we'll start at point P. We'll make our way across this middle section and then back around on this lower section until we've returned where we started. So in this case, the first thing we're doing is going across the internal resistance of the second battery in the direction of the current, so we have minus I2 times little r2. The next thing we're doing is going across the EMF from negative to positive, which means we have a voltage increase, epsilon 2. And then finally we loop back around until we get to the starter motor. And in this case, we're going in the same direction that the current is flowing. So that's minus I3 times R sub S, and that equals 0. So those are the three equations that we're working with. The next thing is just to crank out the algebra, make sure we get the right answers. Okay, so to continue this, here, let's label the three equations I just wrote down as equation 1 for the junction rule, equation 2 for the first loop rule we did, and then equation 3 for this one. So what I'm going to do to start off is actually plug in the known values, starting with equation 2. Okay, so equation 2 says we have minus I1 times Rj, which we found earlier is this number, 0.00257. All right? Then next we have minus I1 times little r1. So that's the internal resistance equal to 0.020. So plugging in this value. The next thing we have is plus epsilon 1, so that's plus 12.5. Okay, and then if we keep going, the next thing we have is minus I1 times Rj yet again. So 0.0257, or I should say 0.00257. Then minus epsilon 2, that's minus 10.1. And then finally plus I2 times little r2, which is 0.10. That whole thing gives us 0. Now, it's not as bad as it looks. It's actually just an equation with two different currents, I1 and I2. There's a bunch of stuff we can start combining here if you take a look at this. So, overall, I have three different numbers multiplying a factor of I1. It's this, this, and this. Let's just add all of those numbers together. And what we have is minus I1 simply multiplying 0.02514. That's what happens when we combine all the I1 terms. Okay, we have actually two constant terms, which are minus 10.1 and 12.5, here and here. And when we combine those, we're going to get positive 2.4. And then I'm just left with the I2 term, which is, again, I2 times 0.10. So what can I do with this? Well, I can eliminate one of the variables. Okay, I can, let's say I want to eliminate one of the variables here. So the way this is going to work is we're going to take, actually now, equation number 1, this one, And we're going to write it this way here. Equation number 1. What we're going to do is write out equation number 1 as I1 equals I3 minus I2. Okay? So why am I doing this? I'm just trying to eliminate I1 as a variable. And so what I'm going to do is take what I just wrote down, which is I1 equals I3 minus I2, and I'm going to plug this into, let's just point to it, this result. All right, so here's what that gives us. We have minus 0.02514 multiplying I1, which we're subbing out in place of I3 minus I2. Hold on a second, guys. I need a new pencil. Okay, yeah, so making the substitution I just said, we're doing I1 is being subbed out for I3 minus I2 right there. And then I have, once again, plus 2.4, and then plus 0.10 times I2. Okay, this writes much better. That equals 0. Okay, let's expand out what's in the parentheses. So we have minus 0.02514 times I3, and then plus that same factor, 0.02514 times I2, just distributing into the parentheses, plus 2.4, and then plus 0.10 I2 equals 0. So if you look here, we have two I2 terms. Just combine them. And so what we're going to get is, all right, I've got a constant factor of 2.4 right here. When I combine these two I2 terms, what I'm going to get is plus 0.12514 I2. And then I'm going to have this negative term, minus 0.02514 times I3 equals 0. All right. So we've already subbed out I1. Okay. The next thing we're going to do is sub out I2 because the current that we actually care about is I3. That's what we want to find. So let's take this negative term, add it to both sides. Let's take 2.4, subtract it from both sides. So we have 0.12514 I2 is equal to positive 0.02514 times I3 minus 2.4, which gives us, if we divide out this factor right here of 0.125 and so on, gives us 0.201 times I3 when you divide out this factor, and then minus 19.18 when you divide it from the 2.4. Okay, so here, let's start by taking equation number 3, or let's finish this off by taking equation number 3 and plugging in what we know. So equation number 3 says we have minus I2 times little r2. So that's going to be minus I2 times 0.10. Then we have plus epsilon 2. So that's going to be plus 10.1. And then we have minus I3 times RS. So that's minus I3 times 0.15. Just plugging in the given values here. That equals 0. But actually, how about we do this? Let's take what we just worked out for I2 and sub that in right here. So I have minus 0.201 I3 minus 19.18. That's I2 times 0.01, or 0.10, I should say, plus 10.1 minus 0.15 I3, that equals 0. Okay. So as a result of all this different substitution, now we have a single equation where the only unknown variable is I3, which at the end of the day is what we care about, because that's the current being delivered to the starter motor. All right. So we're on the home stretch on this one. We've got, if we distribute the 0.1 into the parentheses, we've got minus 0.0201 times I3. And for the second term, because we have two negatives, we have a positive 1.918. Then we have positive 10.1. And then we have negative 0.15 multiplying I3, all equal to 0. Okay, so let's combine things. Let's combine the two terms with an I3 in them. So this and this. When you add those numbers, you're going to get minus 0.1701 I3. When you add these two numbers together, you're going to get plus 12.018, and that's going to equal 0. Okay, so we can see how to finish this off. Take this negative term, add it to both sides, then divide by 0.1701. So I3 is going to equal 12.018 divided by 0.1701. That equals 70.65 amps. And actually, I haven't been keeping track of the sig figs as we go. It just gets kind of too cumbersome to do that. But at the end of the day, we should be rounding this off to 2 sig figs. And that's going to give us 71 amps. So compare those two numbers. Okay, when we only had the weak battery connected, we were only getting 40 amps worth of current going to the starter motor. So that wasn't enough to get the car going. But in this case, we have 71 amps, and that could be good enough to actually start the car. All right. So we're going to keep it moving with a question for the class. And in this case, the type of circuit we're looking at doesn't involve resistors and batteries. Instead, it involves capacitors and batteries. But what I want to show you is you can actually analyze a circuit like this, something we saw way back in chapter 24, using the exact same rules that we've been talking about, Kerkoffs rules. Okay, so for this circuit shown, we're going to do the following. We're going to, step 1, apply the junction rule at point P. Step 2, apply the loop rule to the innermost loop of the circuit, starting at point P and going clockwise. So let's just indicate what that is. So I'm going to start here. I'm going to go this way, all the way around to the battery, and then back down here, so it's the innermost loop, and then back to point P. And then step 3 is we're going to take the loop rule, starting at point P, going clockwise, but this time we're going to take the biggest possible loop, which is the outside loop. So we're going to go around this way, across the battery, just like before, except now we're going to go across the top, and then back to point P. So we're going to have 3 equations, and as you can guess, there are going to be 3 unknown quantities, but they're going to be actually values of Q, electric charge, as opposed to current that we solve for in this case. All right, so let's work it out. So this is our circuit right here. And just to indicate, this is the point P that we talked about earlier, where we're going to apply the junction rule. And let's start there. We're going to say, apply the junction rule at point P. All right, so in this case, think of the junction rule as saying that any charge flowing into point P is going to equal the charge flowing out. Okay, so let's think about this. Before we connect these capacitors to a battery, there isn't going to be any electric charge on any of the plates. It's only when we connect it to a battery and charge starts moving around that we have any charge on the plates. Okay? So these two plates, minus Q2 and minus Q1, well, they end up with a negative charge. So if you think about what that means, in terms of conventional current, these plates becoming negative means positive charge is moving this way. So that would be into the junction, right? If I have positive charge moving off of these plates, it makes them negative. So, okay, what would that charge be? Well, we have Q1 and Q2. Okay, so some positive charge flowing off this plate and off this plate gives it the negative charge as you see here. And then the charge flowing out of point P would be going to the positive plate of capacitor number 3. So that would be Q3. So it's the same kind of idea that we applied for currents, except just for electric charges. It still holds true, because the entire basis of the junction rule is conservation of charge. All right, that's our first equation. The second one is this. We're going to take the loop rule, apply it to the outermost loop, or sorry, let's do the innermost loop first. And we're going to start at point P and go clockwise. Okay, starting at point P, going clockwise, the first thing we encounter is capacitor 3, which has charge Q3 on its plates. Now, since I'm going from the positive to the negative plate, just like if this were a battery going from the positive to the negative terminal, that is a negative voltage. So minus Q3 divided by C3 is the voltage I get going across this capacitor. The next thing I do, following this loop, is I go across the battery. And in this case, I'm going from the negative to the positive terminal, which is a voltage increase, plus V battery. To complete this loop, I'm going to follow this around, and now I'm going across capacitor number 1. And what's happening here is we're going from the positive to the negative plate, which is a negative voltage, minus Q1 over C1. And then we make it back to point P, so that's the complete loop. All right, now the last one. We're doing the loop rule. We're going to do this for the outermost loop. Okay, so the first part of this loop looks exactly the same. We're going to start at point P, go across capacitor number 3, which gives us minus Q3 over C3. Then we're going across the battery just like before, which gives us positive V battery. But now we're going across capacitor number 2 to complete the loop, which is minus Q2 over C2. That equals 0. So what do we have here? We have 3 independent equations, okay, generated using Kerkoffs rules, and we have 3 unknown charges. So plug in the values. C1, C2, and C3 are all the same. Those were all 3 times 10 to the minus 6 farads. Our battery voltage was 4 volts. So I'm not going to go through the algebra here, but if you work it out, you solve the system, you're going to get Q1 equals 4 microcoulombs. Then you're going to get Q2 is also equal to 4 microcoulombs. And then finally you're going to get Q3 is equal to 8 microcoulombs. Those are the answers. Now you could have solved this problem by using methods from chapter 24 involving equivalent capacitance. Try to combine these 3 things into a single effective capacitor and you'd get the same answers. I'm just showing you here that you can actually apply Kerkoffs rules to a problem that we've seen in the past. Okay? So that's it for today. The next lecture is going to be on RC circuits, so I'll see you then.